Okay, so let me say a little bit about stable populations. All right. So I will focus on the example that he gives in this section. If you remember, we have wild animals, and they're in a reserve or a park, and then they interact. They freely go in and out of the park, and this relationship captures the wandering of the animals in and out of the park. So here we have Pn plus 1 equals 0.90 Pn plus 0.01 Rn, and Rn plus 1 equals 0.1 Pn plus 0.99 Rn. This encapsulates the fact that of the population at time n that's in the park, 90% remain in the park and 10% go out of the park. Of the population that's outside of the park, 99% stay outside of the park and 1% go into the park. So what this kind of shows you that you can almost see right away is that the population of the outside is going to be 10 times bigger than the population inside, because that's the only way to make the in and the out balance. I should say, in order to balance the populations so that they don't change, the population outside of the park will have to be 10 times bigger because the outflow from the park would have to be the inflow to the park. Now, another thing I'd like you to notice about this is that in this model, the populations won't change, right? Because this says 90% of the population, 90% of the population inside the park stays in the park, 10% goes out. That makes 100%. So the total population doesn't change. Here also, the total population doesn't change. 1% of the park outside, population outside goes in, and 99% go out. So the total population cannot change. All right. So here does the case of a stable population when then from time to time there is no shift in the balance between inside and outside the park. I mean, you may start out with all the animals inside the park, and then slowly, they're going to leak outside the park. But eventually, you'll reach some kind of equilibrium. Right. So, and he's in this case, he does start in the equilibrium. But if I had started with small p equals 10 and p0 equals 10 and r equals 100 or 1,000, you would have some shifting in the populations until they equalized. Right. Now, if you look at this example, he solves for the eigenvalues, and one of the eigenvalues is 1, and one is 0.89. Now, what does 0.89 mean? 0.89 would mean that, so suppose I had the eigenvalue 0.89. All right, so let me do that here in my document. Okay. So I'm, okay. So here I have what we call a transition matrix. Let me use my blue pen again. So this one is going to be population. Okay, and so this was Pn plus 1, Rn plus 1 is equal to, we remember that 0.9 stayed in and 0.1 went out. The columns add to 1, it's a stochastic matrix. 0.01 go back, 0.99 stay outside, and then this was Pn, Rn. And as I said, if the sum starts 1, if the sum of these starts, I'm sorry, the sum of these two doesn't change. If I start with 1,000 animals, I'll have to end with 1,000 total animals. Now, if we have two eigenvalues, we have lambda 1 is equal to 1, and lambda 2 is equal to, I think it was like 0.89. Okay, so what does 0.89 mean? 0.89, that implies that Pn plus 1, Rn plus 1 is equal to, well, this is T times Pn Rn. Okay. All right, so I should say that in this case, if we have the eigenvector, so let me write this again. let me just be clear about this so that I'm showing you what this. So let's just call the eigenvector, in this case, the eigenvector let me just call it P prime and R prime. Okay. All right. So what does P prime R prime satisfy? P prime R prime satisfies P prime R prime is equal to, and this one we call, what did he call this? I think he called it T. Did he call it T? Yes, he called it T. All right. P prime R prime is equal to T times P prime R prime. But since it's an eigenvalue with this eigenvector with this eigenvalue, that's equal to 0.89 times P prime R prime. Okay. All right. So that means if Pn is equal to P prime and R prime and Rn is equal to R prime, that implies that Pn plus 1, Rn plus 1 is just equal to T times Pn Rn. Okay. And that's equal to 0.89 times Pn Rn. Right? Okay. Okay. Now, suppose I take the sum of the components on both sides. That tells me that Pn plus 1 plus Rn plus 1 is equal to 0.89 times Pn plus Rn. Right? Now, what does that tell me? The total population has decreased by 11%. Okay. Now, how can that be? But we already know that the population can't change. Okay. So how can this be? Okay. All right. So what you find out is that the solution has a positive and a negative component. So the solution for P prime R prime has either P prime is less than 0 or R prime less than 0. In other words, you're starting with a negative population. And the negative population is canceling out the positive population. Now, clearly, that's practically impossible. All right. So this is a mathematical solution, but it cannot be achieved in practice. Okay. All right. Now, this is really not so unusual as you might think, because we often have polynomials that have complex solutions, and if we may have a real problem, and a polynomial that has complex solutions cannot correspond to a real solution of the problem. All right, if a polynomial that's the result of a equation in physics, and you get a complex solution, you can know that that complex solution is impossible in practice. Mathematics doesn't tell you whether it's possible in practice or not. You have to impose those constraints on it. You, with your intelligence, you have to know that the solution has to be positive. Let me see if there's anything else I want to say here. Other than that, I think there's really nothing new here that will cause any issue. Oh, yes. All right. So let me do the second one. And the second one, what's that all about? All right. So what will happen to the population in the park in the event of a growth of an external population of 1% per year? All right. So what does this mean? So we get new equations. Okay. For that relate Pn plus 1 to Pn. Well, Pn and Rn plus 1. Okay. Now, what about Pn plus 1? Well, Pn plus 1, we still have 90% coming from the park. We still have 1% coming from outside. Rn plus 1, we still have 1%. Let's see. We still have 10% coming from the park. And we still have 99% going to the park. Okay. Did I do that right? Yes. 99% remaining in the park. But now we have 1% growth. Okay, so this is the new aspect here. Now we have 1% growth. All right. Now all this does is change the T matrix. Okay. And the matrix is no longer stochastic. Okay, the columns do not sum to 1. All right, all right. So so 1 is no longer an eigenvalue. But this is what you expect. If you have population growth outside the park, well, the population inside the park is going to grow as well, right? Right. So, so here he wants you to do some numerics to see how it's going to change, but you'd expect that to change. Now, if you looked at the answer key is wrong. Okay. So just beware there that answer key does not give you a correct answer. And anyway, you shouldn't be relying too heavily on the answer key. So what else do I want to say? I think page ranking was not a problem. And I talked about linear recurrence in a different video. The equation here, in case you missed that, this should not be here. I'll just write it out so you can see it explicitly. This is not correct. It should be Fn. The coefficients do not depend on n. And since there are k coefficients, you just number them from 0 to k minus 1. Okay, so I should say f of n is equal to a k minus 1, f n minus 1. Now, the f's are consecutive, so the f's still involve the n's, but the a's remain fixed no matter what n is. So this is ak minus 2, f n minus 2. And then this goes up to a0, f of n minus k. Right. Now, one of the equations was you want to show, the way he writes it is show that f r I, rj of n equals rj to the n is a solution of this recurrence relation. Where rj is a root of this polynomial lambda plus lambda to the k plus a k minus 1 lambda to the k minus 1 plus dot 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 plus a0. All right, now the answer key says induction. You don't use induction. What you want to do is you want to want to show, you simply want to plug this value in for Fn. You want to plug rj to the n in for f of n. That's all. And show that the equation is satisfied. Now, There's one caveat because you can't have f less than 0, so you'd have to say for n greater than or equal to k. So I think one of the confusions here is also apparently the confusion in the book was that you have to get the difference between n and k. N is sliding. N increases. The minimum value of n is k, so you'd have k plus 1, k plus 2, k plus 3. N is variable, but the k is fixed. K is the fixed length of the recurrence relation. That does not change. Just like in Fibonacci sequence, you have a fixed length of 2. So in that case, the length of the recurrence relation is 2. So k is the length of the recurrence relation, and that does not change. Other recurrence relations may have more terms, but that length does not change. All right, so hopefully that clarifies things a little bit there.